I want to really thank you for finding the time, and to all of you friends of the CBM². I'd like to introduce Dr. Shaowei Ding, who is a senior research scientist at TerraPrint. This is the company that is well, commercialized actually, this desktop micro and nanofabrication technology developed by Professor Chad Merkin. Dr. Ding earned a PhD in mechanical engineering and also has a master degree in agricultural and biosystem engineering from Iowa State University. Uh, um, Shaowei is an expert, and that expertise spans optical, electrical biosensing, solid surfaces, biofunctionalization. Um, and that expertise, I think one of those, right? That's what brought you to the company. So you can actually develop using the band pen beam pen lithography. You can develop those applications across biology, chemistry, physics, and of course, material science. I am really excited to hear, and the title of the presentation is Beam Pen Lithography for Rapid Maskless Nanopatterning for Organic and Inorganic Materials. The floor is yours. Thank you. Thank you, Shaowei.
Yeah, yeah, thank you for your invitation. I'm excited to talk about this tool. It's very powerful. My name is Shaowei Ding, a senior research scientist at TerraPrint. We are a nanotechnology company that got established in 2015 within the campus of Northwestern University by our co-founders, Dr. Chen Merkin and Dr. Andre Ivankin. Today, I will introduce beam pen lithography, a breakthrough tool for rapid and maskless nanopatterning of both organic and inorganic materials. So before BPL, one important milestone was deep pen nanolithography, or DPN. Some of you might have heard of this. It actually transformed the AFM, the workhorse of nanotechnology, from a purely characterization tool into a nanoscale lithography platform. By using the tapping mode of an AFM tip, it transfers molecular ink onto a subsurface. DPN enables true nanoscale resolution and worked with a wide range of functional inks, from small molecules and biomolecules to polymers and nanoparticles. However, DPN still has several limitations. It is fundamentally built on AFM hardware, which means users often need specialized training and nanoscience expertise. It is low throughput. One tip writes one feature at a time, and the probes are relatively expensive, making scaling very difficult. Here I'm showing you the entire TerraPrint toolbox. This is the tool that is here at Kansas, the middle one, beam pen lithography. I will focus most of the remaining time to talk about this one. In addition to this tool, TerraPrint also sells PPL and maskless photolithography tools. I want to briefly talk about all of them because they are kind of related to each other. The first one is polymer pen lithography. As what I mentioned on the previous slide, DPN has some drawbacks because the throughput is low. There was only one pen that drags ink to pattern across a larger surface. To overcome the challenges, we further developed polymer pen lithography, which powers our TerraFab T series. It introduced 100,000 parallel probes for high throughput, scalable nanofabrication. PPL dramatically improves throughput, but it's still a form of macro contact patterning. All pens in the array pattern the same design simultaneously, so each pen cannot be addressed individually. You can see the SEM image at the bottom left. It's 60 nanometer. So by applying different force using the elastomeric stamp, you can vary the feature size and pattern within a larger surface. And then to overcome the limitation of individual addressability, researchers introduced a clever modification. They coated the entire pen array with a thick gold layer, making it optically opaque. And this is how you get beam pen lithography. They open a tiny aperture at the very tip of each pen. This allows only one nano-sized beam of light to escape from each pen tip. On the back side of the array, a digital micromirror device was used to project programmable light pattern onto the pens. This means each pen could now receive its own light signal, enabling the pens to act as thousands of individually addressable nanobeam emitters. Well, for the last one, we have developed another maskless lithography tool designed to operate over wafer scale. So right now I'm popping up 3 instruments at the bottom. You see the first two, it has a beam array, a pen array inserted between the objective lens and the stage. While for the last one, it's just an objective lens that's focusing onto the substrate, and it has automated stitching function. So it's able to enable wafer scale patterning. So right now, let's officially meet the TerraFab E series. This is a tool at your facility. What makes this system powerful is its high throughput nanopatterning enabled by the active probes. There are more than 30,000 individually addressable pens, each capable of guiding light down to the nanoscale. This allows users to pattern continuously from the millimeter scale all the way down to 250 nanometer resolution without changing the tools or masks, just by applying different force or different exposure time or switching operation mode, which I will cover on the later slide. Each exposure covers 4 by 5 millimeter writing field. We currently, for your instrument, we have 4 or 5 nanometer and 532 nanometer light source. And the light intensity is up to 430 milliwatt per square centimeter, which enables fast patterning speed even for thick or less sensitive materials. This is the non-traditional photolithography tool, as you can see. It's a maskless tool. So let's start the talk with something you guys might be more familiar with, the traditional photolithography. Photolithography is a crucial process in microfabrication, using light to transfer patterns onto a substrate. There are common tools such as SAS, MJB4, and SAS MABA6. The first one is a contact-based mask aligner, while the second one is a projection mask aligner. For the last one, MLA150 is from Heidelberg, also maskless and direct red lithography, but the number of pens is limited, so throughput is a little bit worse. And on the left, you see the flowchart of the general photolithography. Usually you have a substrate with a layer of metal. You coat the metal with some photoresist, and after exposure, the exposed metal can be etched away or post-processed, so you will have your desired metal pattern. That's like really general. And also there are like 2 types of photoresist people usually use. For the positive one, after exposed to light, the exposed area will be developed and washed away. And on the other side, you have the negative photoresist, such as SU8, and after exposed to light, the developed area will stay onto the surface. And there is like a lot of applications with both photoresist. Now we look at the photolithography in the TerraWay. As what I mentioned before, the TerraFab E series comes with 2 modes. The first one is the nano mode, the BPL mode, where you use the beam pen array inserted into the instrument, and you have 30,000 up to 100,000 nano beams of light, and you can get sub 250 nanometer resolution based on the size of your aperture, like the small image at the bottom left. The smaller the aperture, supposedly you can get higher resolution, but this is one of the limiting factor about your patterning resolution. When you apply different force and also different exposure life, different exposure time, this is something you can fine tune. Say you have a lighter force and a shorter exposure time, you can achieve even higher resolution than the light guide shows. And on the right, there's a macro mode, the DMD printing. In this mode, you are not using the beam pen array. So you swing that array holder out of the system and you can directly use 2 million macro beams of light and project onto the substrate directly. And you can achieve around 1 micron resolution based on your choice of objective lens. So before you start an experiment, you need to know like what pattern size, what pattern resolution you want. And this can help you to select which mode is more beneficial to your research. And now there are some selected application with Terafab E series I want to highlight. This can help you to motivate you in your research to some extent. Two of the most powerful aspects of these tools are their maskless capabilities and their materials versatility. Two features which lend themselves very well to device fabrication, specifically microelectronics and wearables. For the section on the left, you see the capacitor and inductor, and there are grids that's separating the entire pattern into many partitions. So during the BPL patterning, each pen can be patterning like one partition, and all of them can work together to stitch a large pattern together to make some very complex patterns. And this shows like a material versatility too, because you can work with a wide range of photosensitive material. And below that two pattern, you see we created gold electrode on the silicon and also photoresist on the PET flexible material. So the versatility is not only for your ink selection, it's also for your material selection. On the right, there are some demonstrations showing the BPL was used to create biopolymers, hydrogels, and biomolecules. You have the ink on the substrate, and after exposure, the cross-link will happen. For the first example, you have hydrogel with different particle size, and on the right, the hydrogel can be decorated with functional group, and you can post-process the matrix to decorate it with protein or DNA, any biomolecule of your choice. And for this slide, there are some more powerful applications that I would like to highlight. The first one is the application of microfluidic devices. This top one is the example of microfluidic gradient mixers. This has two sources of ink, two dye, and they can be merged, showing a gradient. And the lower one, you have dPCR device and macroporous membrane that can be used for like tissue engineering. In the middle, you have this map, Chicago map. It's patterned using the actuated BPL mode. It took 30 minutes to finish with a resolution of 800 nanometer. It's not really application for like a scientific application. It just demonstrates the complexity and also the precision we can achieve within such limited space. And on the right, this is the work from CUNY University of New York. They synthesized different glycan and brush polymer using beam pen lithography, and they use like a cyclic experiment to introduce different polymer, and by control the time of growth, they can change the linear polymer's length and vary the gradient. And of course, there are a lot more applications and capabilities. If you guys want to go into certain application, I can spend more time after the talk. And another thing I want to highlight is this instrument also has limited capability with polymer pen lithography. The first technology I introduced on the earlier slide. We have an elastomeric stamp, and on the surface, if we coat it with gold and introduce a small aperture, we can use that for photolithography purpose. And if we don't have any coating, you can just use it as a macro pattern, macro stamp. On the surface, we can introduce different source of ink and pattern inorganic materials, or we can create like a metal circuit on the silicon surface, or well on the right, you can create different patterns using small molecule and get the growth of cell study. Well, for the last one is the block copolymer. We used force alignment instead of electrical alignment and realized high uniformity and coverage on a large substrate. What makes Terafab better? This is a comparison chart that looks through different technology. For the TerraPrint technology, we have advantage in a lot of them, but we are not saying we are the best. It's just like a really good combination. Terafab technology has three main like features. The first one is the dynamic feature size control. Feature size can be tuned on demand by adjusting exposure dose and tip deformation, enabling flexible nanoscale patterning without changing mask, optics, and materials. Second one, we have materials compatibility. As a direct red optical technique, BPL works with a wide range of photoresist, polymers, monolayers, and light-driven chemistries, allowing both structural fabrication and surface functionalization in a single platform. We also have high uniformity because BPL delivers light directly through tip surface contact in the near field. The pens automatically compensate for local substrate height variation, providing more uniform feature quality than conventional projection-based tools. After going through all of the fundamental knowledge, we have a general idea of the instrument. Now we can move into the instrument workflow, and I will introduce more about the technology. So here is the operating mode for E-series. I talked about we have two modes. The first one is macro mode, DMD printing. The second one is nano mode, BPL printing. Before you start your experiment, I'd like to emphasize again, you want to know your resolution, like your desired resolution. If you need something higher than 1 micron, you can use the DMD mode. The resolution you can achieve 5 micron, 2.5 micron, and 1.25 micron. You just need to prepare your sample, make sure the sample is flat, and there's no need to go through electrical alignment or optical alignment. You just need to design your pattern in a design software such as Adobe Illustrator. You create something that's 1024 by 768 pixel, and then save it as a PNG. You just upload and finish the pattern in seconds. If you need something that's at maximum 2 micron and to sub 500 nanometer, this is when you want to use the nano mode, the BPL mode. You want to prepare a substrate that's flat with clean cut edges, and you will go through electrical alignment or force alignment to make sure your substrate is in parallel with the array. And then you align the 30,000 beams to the back of the pen array to make sure the pens can be individually addressable. And then you go to the pattern design, you calculate your feature size and the entire pixel size, the entire image size. You upload and do the patterning. This can generally take longer than the DMD pattern because it's more complex, more information dense. For this experiment setup, this is like a universal requirement for all photolithography tools. You want to make sure your substrate is clean and flat. And for the material selection, you want to know how well your photoresist adhere to your surface and the aspect ratio and film thickness of your pattern. Since our light dose is, the light source is 4 or 5 nanometer and 532 nanometer, you want to make the decision like what photoresist can work with this wavelengths. There are some commonly used photoresist for our instrument. For example, SU8 is a form of negative photoresist. We generally use it for the macrofluidic setup, and it comes with different like a thickness. So you want to make the choice based on your experiment. And also there's S1813 or S1805 that are more generally used for macroelectronics application. And this one is a positive photoresist. Also, there are preparation conditions such as spin coating, spray coating that's used to generate the uniform layer of photoresist or photosensitive material. And you want to make sure, like if there's any pre and post bake needed for your experiment. And here's the image for the BPL patterning. You have an array, and this array you see in the image. You want to go through the first physical alignment to align the substrate to the array to make sure this substrate is in parallel condition to the array. Then you go through the optical alignment to align the light to the back of the tips. And this is the general overview of the instrument. I'm showing you a video here. It's showing all of the electronics box component. And when I double click the software, it will initialize and establish connection to the computer. Now we move to look at the enclosure. This is the entire setup. The top portion is the optics, and we have a camera that's showing you the live image. For the next image, this is the optics part, and you have an objective lens, and it's motorized using this X and Y motor to move it horizontally. And you also have this lab jack that's moving this objective lens vertically to focus onto the back of the beam pen array. For this image, it's showing you the sample holder. And there is a stage. We put the substrate onto the stage. This stage is protected and monitored by a force sensor. This force sensor can read very accurately. It protects your entire assembly, and also it tells you the real-time force when you are doing the BPL patterning. It's very sensitive, so make sure you don't want to go beyond 4,000 millinewton when you are using it. And there is a piezo motor that can move the substrate up and down during the BPL patterning. And it's very accurate, having resolution accuracy of 0.1 nanometer during movement. I'm showing you the video. This is to demonstrate how I load a sample onto the stage. I'm being very gentle because I don't want to cause like a sudden increase of force. And I'm also aligning the substrate. So all the edges in parallel to the stage. And after this step, I'm closing the array holder and it's ready for the physical alignment. This is the array holder. So you see in this picture, I'm detaching the bottom of the array holder. And the array can be inserted facing down inside the array holder. Make sure your hand never touch the bottom of the array, because that's the part you want to make sure it's clean and it will be physically aligned. After we set up everything within the instrumentation, everything is ready for you to initiate the automated alignment feature. On the array, you have multiple electrodes, and when they are in contact with your substrate, it will complete a circuit indicating one of the corners light up. And the instrument will go through coarse and fine adjustment until all of the corners are in perfect contact with the array. This entire process is automated. And after you establish the physical alignment between the array and the substrate, we want to make sure all 30,000 probes are in contact with the substrate. And first, we use the bigger window of light, and you see every single projection might look different when you first start the projection. And we want to use the rotation setup to rotate all of the projection until they look identical. Next, I'm changing the projection of light into something smaller. We have a light guide or a small aperture at the very tip of each aperture. So supposedly if no light is being reflected back, they are going through the light guide, and that's showing like a perfect optical alignment. So when this window shows like this, it's showing some of the light is being reflected from the wall of the pyramid, and I'm moving the light using X and Y movement, the motorized movement, until the screen turns completely dark. And now it's ready for the pattern design. There are some like easy pattern you can do with non-actuated printing. The reason we call it non-actuated is when all of the pins are patterning the same exact pattern. It's repeated pattern. When it's very easy, a dot matrix pattern, we call it, we will just use it, design it in the software. When you need something more advanced, more complicated, like this TerraPrint pattern, that TerraPrint logo, QR code, you can design this in Illustrator software or any other design software. You can change the grayscale based on the force and dwell time, the exposure time, to vary the gradient. Or in some application, you want a very complex pattern, like this Chicago map. Or when you want all of the pins are patterning something different simultaneously to create like a different condition for your experiment, you want to use this actuated printing. You can set your like a moving speed of your motors and exposure time, and the computer will automatically create partition and interpret your experiment and create your result. For this image, I'm just showing you a general overview of all the patterns that this instrument is capable of creating. So for macro mode, for the DMD printing, it's when you don't need your resolution very high, say above 1.25 micron to 5 micron or 10 micron as your feature size. You can create microelectronics and microfluidics. This is, I treated the positive photoresist after patterning. I treated with e-beam evaporation to create gold electrode, or you can use SU8, the negative photoresist, and create PDMS, DPCR microfluidic device. Or if you need some conductive pattern made with this setup, you can just use SU8, and after high temperature pyrolysis, you will have a conductive pattern. Or in some case, you want to use BPL mode when your resolution is sub 1 micron or sub 250 micron. For this actuated BPL, every pin is patterning something different, or they can be used to stitch a more complex pattern. While for the non-actuated pattern, you can create dot matrix or QR code or something like identical and repeated. We have application notes available by request, such as microfluidics, biopatterning, hydrogel patterning, and microelectronics application. We have them internally. It's not official, but I'm happy to share. Well, thank you all for joining the talk today. I'm happy to revisit any slide or dive deeper into specific applications if you are interested. If you have ideas for projects or collaboration, we would love to discuss them. We have supported joint development efforts before. We also have several application notes, like as I mentioned here. They cover like a wide range of things. Or if you have any other questions, feel free to send an email to me. And this is my talk today.